Hello there, this is the third in a series of screencasts on the subject of redox chemistry for the module CHE10063. Okay, so today what we're going to do is we're going to put together what we've done so far, where we've been talking about different types of redox reactions and how we can write them. And now we're going to actually understand why it is we need to write redox reactions as half reactions, because by doing that we can make predictions as to what reactions are actually going to occur spontaneously. Okay, so that's the main aim of today, is to identify spontaneous reactions through considering the half cell reactions. Okay, in terms of reading for this, we've basically got these two books that I will point to here. So you've got Inorganic Chemistry, and there's a few pages from that, and this QR code takes you to page 188. And likewise, probably the more bulk of the reading comes from Elements of Physical Chemistry, which is obviously more directed at the sort of calculation side of things, so the predictions needs calculations, and you know, again, this QR code will take you to 227 and you can go forwards from there. Okay, so the underlying thing that we're going to have to think about is how to define whether a reaction is going to proceed or not, or if it's going to proceed spontaneously or not. And in order to do that, we need to consider the standard Gibbs energy of the overall redox reaction. Okay, and that's this value here, sort of delta Rg cell. Yeah. Now the key point for a redox reaction is we can calculate that when we consider the standard Gibbs energies of the individual half reactions. So this is the one for the process by which things are being reduced, the species are being reduced, and this is the one where the species is being oxidized. And obviously we've got some examples from that from the previous lecture already. Okay, the key point is, in order to actually define these, get these values, we actually need to set a definition point. Okay, and in order to do that, there's a definition point, which is that this reaction here, 2H plus 2E minus goes to H2, that has got a standard Gibbs energy of reaction. For that half cell reaction, that is a standard Gibbs energy of 0 kilojoules per mole. Okay, and so every other half cell reaction, the standard Gibbs energy of that any other half cell reaction is basically quoted in relation to this one here. Okay, and this is also the hydrogen electrode, and we'll talk about different types of electrode slightly later on in this screencast. Okay, key point here, which ties the standard Gibbs energy to something we can actually measure, which is this thing here, is basically that the standard Gibbs energy for each half cell reaction is equal to minus the number of electrons being transferred. So in the cases one of the cases we saw so far, that was 2, wasn't it? Okay, the first case, and then for our manganese, I believe it was maybe 10, if I remember rightly. Times by Faraday's constant, which is given down here, and note that this is coulomb per mole. So in this case, you know, you need to multiply that by 1,000 before you can actually use this. Multiplied by this thing here, and this is the standard reduction potential for the reaction, okay, or the standard reduction potential for the half cell reaction, you know, okay. So, you know, this is always the case, and we can measure this, and I'm going to explain how we measure that on the next few slides. Finally, we need to remember that if we have a spontaneous reaction, or if we can determine, in order to determine whether a reaction is spontaneous or not, we have to look at the value of the delta G for the reaction. Okay, and if that value is a negative, then the reaction is spontaneous. If it is positive, then it is non-spontaneous. If the delta G is a negative, then the reaction standard reduction potential for the whole reaction is going to be positive. Okay, because of this relationship here. Okay, so the key point is we've got to be able to measure this reduction potential, okay? And the way we do this is using electrochemical cells. So there's two different types of cell, one of which is a galvanic cell, and this is where you have a spontaneous redox reaction which will generate an electrical current, okay? So that's one that's actually spontaneously occurring, okay? So that's one type of cell. The other type of cell is an electrolytic cell, and this is where you have a non-spontaneous redox reaction. So this means that in order to get the redox reaction to actually occur, you need to put energy in, and of course you can do that by actually applying a current. So, for example, electrolytic cells are used often in things like aluminium plating, for example. But generally speaking, when we're talking about measuring our standard potential, we're going to be talking about galvanic cells for spontaneous processes. Okay. There's a bit of definitions here. We need to remember that when we have a cell, we have to define our anode as being on the left and our cathode as being on the right, and there needs to be a potential difference between the two cells in order for any current to actually run. Okay, so here we have a typical two-compartment galvanic cell. We've got the anode on the left, the cathode on the right, and you can see here that basically we've got the opportunity for current to flow here. And then you have this, which is called a salt bridge, which is whereby ions can flow to. Okay. Key point physics is that electrons will flow from the anode to the cathode. Okay. So that's a key point, and that makes sense, doesn't it? Because electrons flow from the negatively charged anode to the positive charged cathode. Yeah, makes sense. Okay. Going to touch upon this. You will get some opportunities to practice this at another time next year as well. But basically, when you are describing electrochemical cells, there's a shorthand method to do this. And again, this is covered in more detail in the book here that I've got a link to. Okay. The key point is we've got to write everything in order. We've got to start with our anode on the left, and we've got different types of lines. So the first thing is single vertical line. That's going to be separating things that are in different phases. So for example, if you have two things in the same beaker, basically, but one of them is like a solid electrode or a gaseous or a gas flowing over a solid electrode, then that will be in a different phase to the liquid in the beaker, okay, and any ions within that liquid. And then, of course, we have this double vertical line, and this is a salt bridge, okay. So, this is an example. So we've got here we have the standard hydrogen electrode on the left-hand side, and here we have a copper metal electrode. And so we have platinum first, and the reason we've got platinum here is because this is the material that the electrode is made out of. Platinum's typically chosen just because it's a very noble metal. It's not likely to participate in the redox process unless you use something that's really strongly able to pull the electrons away from platinum. Okay, then of course you have your H2 gas, you have your H+, both in this area here. So you're going to have H+ ions in the solution. You've got your H2 gas, which is flowing over the anode. Okay, then you have a salt bridge, and on this side here in the green area, you've got copper 2+ in the aqueous solution, and the electrode in this case will get made out of copper, solid copper. Okay. And of course, if you have an electrode made out of a material that's actually participating in the redox process, that electrode will obviously disappear over time. Okay, and this is another one. It's a slightly more complicated example, but this is actually an example that was from the textbooks that I've asked you to look at in the quiz as part of the quiz questions. Okay, so you have here, your platinum electrode on the side, and this is called a platinum redox electrode, and again I'll show you what that means in a minute, but basically it's a bit of platinum metal shoved in the solution of, in this case, Fe2+ and Fe3+ anions, and of course there's going to be a reaction between the two of them because that involves a redox reaction going from 2+ to 3+. There's a salt bridge again. Okay, so that's this bit here, and on this side we have the manganese cell. Okay, and so the manganese side we have all of these species all in under aqueous conditions, and in principle really H2O should have a liquid state symbol next to it. I've forgotten to put that in. And of course again we have another platinum redox electrode. Again, the platinum is not actually going to take place in the redox reaction, it's just providing a conductive surface essentially. Okay, but that's essentially how we would describe electrochemical cells in shorthand, and I'll give you I'll get you to practice some of those examples in the quiz. Okay, so we're going to talk a little bit about different types of standard electrodes, just because it's worth knowing how to measure these things. Okay, so the first one is a standard metal electrode. So this is just going to literally be, this is, for example, the solid copper electrode that we were talking about in the last slide. This would be copper metal in this case, or zinc, or indeed any metal that's participating in the redox process, dipped into a 1 molar and this is where the standard conditions come into play, solution of its ion. So, in the case of copper, that would be copper 2+, of course. Second type of electrode is a standard redox electrode. So this is the example we've seen a few times on the previous slide. You essentially have platinum, which is not taking part in the redox reaction at all. It's just carrying electrons or carrying charge, which is dipped into a solution, 1 molar solution of each of the ions. Okay, so 1 molar of each of these things. And finally, we've got a standard gaseous electrode, and the hydrogen electrode is an example of this. Okay, although it's not the only type of standard gaseous electrode. Again, this is going to be a 1 molar solution of ions of the gas. So in this case, 1 molar solution of H+, and the gas is bubbled at 1 atmosphere. Okay, so again, this is all to do with the standard conditions. And if you remember, the delta G of the standard hydrogen electrode, which is this 2H plus 2E- goes to H2, this is defined as having a delta G of reaction equal to 0, which means that also, by definition, the standard reduction potential has to also be 0 volts. Okay, if you think about the equation we talked about on the first slide I went through. Key point, so we've already kind of covered this, but I just wanted to put this very clearly, is that standard is referring to the conditions, and that means that all solutions are at 1 mole per decimeter cubed. So that means that if H+ is at 1 mole per decimeter cubed, that the pH is equal to 0. And you can prove that to yourself. You should be able to do that. Okay, standard pressure for gases is 1 atmosphere. Temperature is a bit more variable, but typically, and this doesn't actually relate to standard conditions, but typically it would be these are quoted at sort of what we regard as room temperature, or 25 degrees centigrade. Okay. So, as we've said already, we're going to use a cell to measure the standard half cell potentials. And I've already sort of mentioned this in passing, but this is all going to be given or expressed against this standard hydrogen electrode, which is defined as having a standard half cell potential of equal to 0 volts, or indeed a standard Gibbs energy of 0 joules per mole, kilojoules per mole. Okay. Of course, this applies when all the components are in their standard states, as we've said on the previous slide. Okay. So then we measure all of any other electrode against this. So essentially we put our standard hydrogen electrode in one of these beakers and put another one in another beaker, and essentially if the process is spontaneous, then in that case we can measure it using a galvanic cell. If the process is non-spontaneous, we can measure it with a electrolytic cell. But what the measurement we're trying to do is a measurement at 0 current flow. Okay, so we're just measuring the potential difference using a voltmeter. Key point here is something that I'm going to reiterate on the next slide, is that the value of this standard reduction potential for a half cell is going to tell us how powerful an oxidizing or reducing agent you've got. So if you have a more positive value of this E standard, then you have a more powerful oxidizing agent, and it's therefore more likely to be reduced. And if you remember oil rig, okay, that means that reduction is gained, so that means that one with a positive value of this is more likely to gain the electrons off of the other species in the full reaction. Okay, so let's have a look at some of the examples of this. So we've got a table here. This is a shortened version of an electrochemical series table. Okay, this is from this page here. It looks a little bit different on the internet version, but it comes from the same book. Okay, and it's got pretty much the same information. A much larger version of the table starts in the resource section 3, and it starts on page 614. So again, this QR code should take you to that position. But you can kind of see we've got these standard reduction potentials for these half cell equations range from, fairly large positive numbers, so like about +3-ish, all the way down to -3. Okay, and as you might expect, if you take fluorine and react it with lithium, then this species, it's going to be oxidized, so it's going to give up its electrons and go back the other way, and that's going to go that way. And this reaction, when you sort of add this together, you're going to get a very big number, and we're going to talk about how to combine reactions on the next slide. But nevertheless, if you've got a big difference and they involve one another, and the reaction involves both species, then it's more likely to have a big value of delta G one way or the other. Okay. As I said already, a position on this table tells us about whether it's a strong oxidizing agent or reducing agent. So, if you have a very big positive value of your standard reduction potential, then you have a strong oxidizing agent, which is very liable to be reduced. In other words, it's very liable to gain electrons. Okay, so fluorine is a very good example of that. So fluorine is a very strong oxidizing agent. Equally, if you've got a very low value of the standard reduction potential, so in this example, you've got lithium solid, for example, or lithium plus. These two reactions here. This means that the species on the right. Okay, so in the case of it being a strong oxidizing agent, it means the species on the left is a strong oxidizing agent. Okay, in the case of it being a strong reducing agent, or the sort of E cell being negative and large negative number, then the species on the right is a strong reducing agent, and the species on the left is, in this case, a very weak oxidizing agent. Although you can kind of see that, for example, calcium 2+ would probably oxidize, would be able to react with lithium, and again, we'll talk about that on the next slide. Generally speaking, and I've been trying to do this as I've been talking through, is that when we are talking about these values, even if they are positive, we say plus 2.87, for example, for the fluorine standard reduction potential, and we say negative 3.04 for the lithium one. Okay, so stating the sign very clearly is very useful, and it's a very good thing to get into the habit of doing, because obviously the sign is very important, and as we will see on the next slide, when we come to add these things together, then it becomes very important again. Okay, so how do we make predictions using this? Well, in order to make predictions of a full reaction, and I've chosen a very extreme reaction here that is very likely to happen, as we will see, and you shouldn't be surprised by this. This is the sort of thing that is the dream of a schoolboy to attempt, because it probably makes a big bang. Yeah, as well. But nevertheless, let's just use this as an example. How do we work out whether this reaction is going to be spontaneous, or, is it going to be spontaneous in the other direction? So, for example, is this arrow the right way around? Yeah. And okay, we have an idea that this is in the right direction already. But the way we're going to do this is by doing what we've done already, writing out the half cells, and then combining them to make a full reaction. So working out essentially with our reaction equation what the component half cells are, and then using these standard reduction potentials to calculate out a value of the potential for the whole reaction. Okay, so let's do that. The first one is we've got F2 in gaseous form goes to 2F minus, and there's going to be some electrons involved in that process, and of course they're on the left hand side. Okay, and so this is the half cell that's within this equation. Yeah, and this has this is going to be reduced by this equation, because you can see that these species are written in the correct direction for the equation as it is written as a reduction. Okay, and we know that this value is this that comes from the table. Okay, in the other case we have the solid calcium metal reacting to give calcium 2+, and in this case this is written in the opposite way to the way it appears in our table, because in our table we're using standard conventions, which as I said in the previous screencast, the standard conventions are that we always state half cells as in the forms of a reduction. So if it's the opposite way round, then it's in the form of an oxidation, and so in this case we have to just kind of say, well, okay, this one in the full reaction is the oxidation. Okay, and again we can kind of see that in this case we've got this as our value, okay, for our standard reduction potential. Okay, so we don't need to change this value at all, we just keep it as it is. This is the standard reduction potential. Okay, now I think I'll just make a slight amendment here, which is essentially that, as you can see, this is kind of the reduction potential, but in the equation below this is actually ox, because this is the oxidized one. But I wanted to make the point that basically you don't have to change the sign, keep the sign the same. Okay, so in this following equation we basically say this is the total reaction potential, okay, and that's given by the reduced form minus the reduction potential, so still a minus sign, for the oxidized form. Okay, so in this case this would be plus 2.87 volts, which is E red, minus and in this case it's minus this. Okay, so a minus times a minus is a plus, so this is effectively means they're both added together. So you get this value for our standard reduction potential for the entire reaction. Okay, and of course from that, we can then say, well, does this mean it's going to be a spontaneous process? And of course it does, because we've already said that the relationship is that if you have a positive cell, a positive standard reduction potential for our reaction for our cell, then you're going to have a spontaneous process. But spontaneity is defined through the Gibbs free energy. So in order to determine spontaneity or not, we really do have to go back and actually either state this equation and say, well, this is positive, so delta G must be negative, or we can actually go to the lengths of actually calculating it out. And that's what I've done here. So I've calculated out delta G because of good practice. Okay, so this is the delta G, which is a very big number, isn't it? I mean, typically reaction delta Gs tend to be in the hundreds, not in the thousands. But this means that this is a very, very spontaneous process if something can be indeed very spontaneous. I mean, spontaneous, it's either spontaneous or not. But, you can see that this is a very large difference in the free energy, which is kind of what you expect just looking at it because of what you know already about these species. Okay, so that's kind of a worked example of how we're going to do it. What I'm going to do now is I'm actually going to go through another worked example in written form, and we're going to actually determine which type of reaction is going to work. But before I do that, I just wanted to have a quick word on units here, because I didn't explicitly put my units in my previous working, and I know that we've been telling you to do that for the past while. The key point here is basically that if you use your F in kilocoulomb per mole, then in that case, your answer for delta reaction G will end up being in kilojoules per mole. And obviously, if you get rid of if you multiply this value by 1,000 first, then you're going to get it in joules per mole. Okay, and then you have to do some calculations. And there's a this is sort of a bit tricky because some of these units are compound SI units. They're not sort of from the base SI units, and so we need to go back to the base in order to actually figure out where it's all coming from. But you should be able to follow this. So V doesn't have any units. This is given in coulombs per mole, which is given as this ampere seconds per mole, and again volts is equal to kilogram meter squared per ampere per second cubed, and then you can kind of follow this bit down here to show that this goes all the way through to joules. And the key point is that kilogram meter squared per second is equal to joules, and you can get that essentially by saying that sort of F is equal to MA. You know what, I'm just going to get a shot of this. Sorry, just bear with me for a second. I just flipped my tablet. So you can basically say F is equal to MA. These are kind of classic, force equations. So that means that, essentially we've got kilograms meters per second squared. And we also know that W is equal to Fx. So it's force times distance, which is, this is this here, and this is distance. So therefore W is in joules. So therefore, joules is equal to kilograms meters squared per second squared. Yeah, and that's that's the same, isn't it? Yeah. Or you can just go to Wikipedia and it does it for you. But it's always better to be able to follow this yourself. So I just wanted to go through a quick worked example of this, and essentially this is sort of the sort of thing we'd like to be able to do using the methods we've talked about. Okay, we'd like to make predictions, and so in this case, what we've got is we've got two reactions and two half-cell reactions, and we want to know, which when we put this into an equation, whether we're going to have zinc being oxidized or reduced in acidic solution. Okay, so we have two options in this respect, really, don't we? And this is just generally a zinc species. Okay, so we have two possible reactions. The first one is if zinc is oxidized. Then in this case, you're going to have this reaction. Sorry. So this is the reaction if zinc is oxidized. Okay, So is that going to work? Well, we can do this quite quickly. We can say, well, if that's the case, then you can see that this one here, the H1, this one's going to be our reduced potential. So we can say E cell standard is equal to this minus, it's got to be minus this one, but of course it is this the zinc one, because obviously in this case the zinc one's going backwards, so it's effectively an oxidized situation. So in this case it's minus 0.76, because this is the oxidized version, 0.76, and the reduced version is 0, and that's going to give us plus 0.76 volts. Okay, and of course you can calculate out the delta G, and I'm not going to explicitly go through the calculation of delta G. It's the same as we did on the last slide. Delta GR standard is going to be equal to minus VFE standard cell, which is going to be equal to, if you calculate it out, it's about minus 150 kilojoules per mole, which kind of makes sense on the basis that this value's you know, quite a bit smaller than the previous value we saw, you know, but probably about 8 times smaller, and so the answer is about 8 times smaller. Okay, so you know, probably on this basis, this is a spontaneous process, yeah, because delta G is negative, and of course, as we'd expect under those conditions, our E cell is positive. Okay, question is, could zinc be reduced? Could it work in the other direction? Well, let's go and have a little look at that one. So we'll start in a slightly different color, go for purple this time. So if Zn is reduced. Now in this case, Zn species on the left-hand side has to be Zn2 plus. Okay, and in this case, it's going to react with H2 gas. H plus aqueous. Oh, I've missed my aqueous here. Plus Zn solid. And of course, you know, if we didn't actually have any H2 gas kicking around, then this reaction couldn't happen full stop. But let's just assume we've got plenty of both H plus and H2 gas. Okay, so is this process spontaneous? Well, we have to do the same thing again. Okay, in this case, we've got E cell, and that is equal to, now the zinc half cell equation is being written in the reduced form, so that's our E red. So that goes first. Minus, and then of course the other one goes second, and that gives us negative 0.76 volts. And unsurprisingly, that's going to give us a delta G reaction standard of plus 150 kilojoules per mole. So that's not spontaneous. Okay, and so we can say that, you know, obviously in that case we can say that zinc metal is likely to react with H plus ions acid to yield H2 and zinc 2 plus, whereas the other way around is not going to happen, okay, unless you apply some current. Okay, so to finish off this idea of making predictions, I just wanted to introduce 2 new terms, which is disproportionation and comproportionation. And these terms relate to the stability of oxidation states of a particular material in solution. Okay, and these are 2 reactions that can kind of spontaneously occur in solution if you start off with a solution of a given oxidation state. So obviously, this is quite an important thing to know if you're trying to perform redox reactions, because it might be that actually those oxidation states you want to use are not that stable, and in the end they will already react before you've actually done the redox reaction you want to do. Okay, so disproportionation is the first example, and this is essentially where the oxidation number, as it says here, of an element is going to simultaneously be raised and lowered. So, you know, we can do an example of this. So an example would be copper plus is going to disproportionate into copper 2 plus and copper 0. Okay, so you know, we can write that out here. Copper plus plus copper plus is going to give us copper 2 plus plus copper 0. Okay, and we can of course, you know, put our state symbols on this. Okay, question is, you know, is this actually going to happen? You know, we can once again prove that this reaction is going to be spontaneous. And of course, in this case, we have two half-cell equations, and we can actually write them out because at the moment they're written out as redox couples, but it'd be better to write this out as a half equation. So that's one of them. And the other one is going to be Cu2 plus E minus goes to copper plus, and again aqueous. Right, so we need to figure out which of these is going to be the reduction direction, and of course it's this one. So if we want to work out our E cell, we can say it's plus 0.52 volts minus plus 0.167 volts, because this reaction here is going backwards, isn't it? In the full equation, it's the oxidized version, and that gives us a total of whatever this one minus this one is. Okay, which is plus 0.36, of course. I'm just going to rub that out because that's not very clear. Yep. Okay, and of course, you know, again, we can calculate out the delta G, but in this case, we can just say delta G 0 is going to be negative because E cell is positive. So therefore, this is spontaneous. Yeah. Okay, so this is likely to happen. So this is a disproportionate reaction that's likely to happen, and it means that copper plus is unstable with regards to disproportionation. Okay. We can do the same thing for comproportionation. Okay, comproportionation is where you have two species in different oxidation states that then react together to give the element in the sort of intermediate oxidation state. So it's kind of the opposite of the reaction we just saw. And so, you know, obviously already you can start thinking, well, wait a minute, if that reaction that we just saw was non-spontaneous, then the opposite of it, the comproportionation, would be spontaneous. Yeah. Okay. So you know we have an example for this, which is silver. So silver plus is a stable oxidation state, and we're going to prove that. So if you have solid silver and silver 2 plus in aqueous solution, they're going to comproportionate to give silver plus. So once again, we can write out our equation: Ag2 plus aqueous plus Ag solid goes to Ag plus Ag plus. Okay, and here we can again find out our E cell, which is okay. So we need to figure out which reaction is which. Again, we can write these out. So Ag plus E minus goes to Ag, and you can put the state symbols in Aq and solid, and again Ag2 plus E minus goes to Ag plus, and again Aq. So clearly the one on the right hand side, this one is going in that direction, and the one in the left hand side is going in that direction. So in that case we have plus 1.98 volts minus plus 0.80 volts, and that gives us plus 1.18 volts, which is pretty big number for our E cell, and it's very positive. Again, we can calculate the delta G, but we can say already that it's going to be pretty large. So we can either calculate the delta G, or we can just say delta G is going to be negative. It's also large. Okay. And actually, if you do look at this process, the equilibrium constant for the process is around about 10 to the 20 at 298. Okay. So you know this is the equivalent of it's the equivalent of an acid dissociation constant. In this case, not an acid dissociation constant. It's just an equilibrium constant, but this would be the equivalent of a superacid in terms of an acid dissociation constant. So this is very sort of favored reaction to go in on the right hand side. Okay,